Afternoon, everyone. So next one is my talk. I'm Yiming Zhang from Southeastern University. Before I joining Southeastern University, I was a Future Fellow from cohort 1. So today I'm glad to share our recent research about edge-oriented lightweight framework for automated pavement damage detection, which is done by my PhD student. So this presentation will be divided into 4 parts. Firstly, I'd like to introduce our research motivation and the current challenges in pavement damage detection. Well, currently, many roads are suffering from different kinds of defects, such as cracks, potholes, and surface damage. Now, we usually collect road images from vehicles, drones, and roadside cameras. However, this system can generate a huge amount of visual data. So sending those kinds of data to the cloud for pre-processing can take considerable time and cannot meet our real-time processing needs. Well, edge computing offers a possible solution for this because it can process the image data directly on the equipment. So road monitoring is not only a detection problem, but also a deployment problem. And we need to develop lightweight detection models that are fast, accurate for edge computing devices. In practice, the defects of pavements are usually small and irregular, such as very thin cracks and the shallow or weak surface damage. A common solution is to use a larger and more complex model to extract better features. But this creates a problem. The model will become very difficult to deploy on the edge devices where the computing resources are very constrained, because when we use the larger model, it has a lot of parameters and can increase the computational cost. So our objective is to develop an integrated design that can achieve fast inference speed and achieve accurate damage detection. Well, the process is very straightforward. A road image is sent to the backbone, and then the neck can combine different features from different levels. And finally, the detection head can identify the damage types and the location of pavement defects. Here we have 3 improvements. Firstly, we use the EfficientNetV 2 as a backbone to reduce the model size. Then we use improved by FPN neck to fuse multi-score information for small and irregular damage. And finally, we use WISE IOUV3 loss function to increase the accuracy and the robustness of the localization of damage defects. In simple terms, this framework converts the road image to different hierarchical features and combine these features efficiently. And finally, the framework can provide a bounding box for damage. More specifically, here we use the EfficientNetV 2 to replace the original UV8 backbone to reduce the model complexity. And in the shallow layers and the deeper layers, we use the different convolution, MB convolution for this. And finally, with these improvements, we can reduce the number of parameters by 18% and reduce the computational cost by 64%. After the After the lightweight feature extraction, the next problem is how to keep or remain the model scale information. Here we first use improved by FPN for combining the different information. Specifically, the high resolution features can help us to detect cracks, while the low resolution features provide more overall context. And then we use WISE IOU v3 loss function to give more suitable attention to different training samples. And finally, our model can provide stronger model scale representation and more robust bounding boxes for the irregular damage. Then we use the RDD 2022 benchmark dataset to verify our model. Well, this dataset collects the defects from different countries. As shown on the left, it includes 4 common types of defects, such as longitudinal crack, pothole, and transverse cracks, where all images are resized into 640 pixels, and we trained the model with 300 epochs and a batch size of 16. Here we not only consider the accuracy, but also the number of parameters, model size, and inference time. So here we adopted different indicators to evaluate the model performance. Well, we did the ablation study first, and as the results are listed on the table, here we can see the EfficientNetV2 can contribute most to reducing the number of parameters, and the BiFPN can improve the accuracy of the detection. And after we combine 3 modules, which is EfficientNetV2, BiFPN, and the WISE IOU, and we got our full model, where the full model can improve the accuracy and reduce computation simultaneously. Then we compared our model to other common models like faster RCN, YOLO V5, V8, and V10, and the models proposed by other researchers. And here we can conclude that the proposed model achieved the highest accuracy, and its number of parameters is not very high compared to other models. So our proposed model can improve the accuracy without excessive model expansion. And to further verify if our model is suitable for edge devices, we test our model on 2 ambient platforms. Usually, the practical inspection videos are commonly achieved at 25 FPS. FPS indicates the inference time. And our model can achieve 28 FPS and 35 FPS on the 2 platforms, which indicates the proposed model can exceed this rate on those both devices. These are the on-device inference results, and from these 4 figures, we can see the model can give very accurate results and stable localization results. To conclude, here in our study, we proposed a lightweight damage detection framework for pavement defects, and it can achieve accurate results with lower complexity. And based on the benchmark dataset, so this model is suitable for deploying on the edge devices. So this is all about our initial study. Thanks for your attention.